All right, so we have chapter 3 here, which is motion in 2 dimensions. All right, so what we're going to do in this chapter is basically continuing with chapter 2, which means we're still looking at pretty much linear motion. The only thing we are now looking at object that can move in 2 dimensions. That means not only horizontally or not only vertically, but also, let's say, such a way that covers let's say position change in both X and Y directions simultaneously. Right. So for example, the graphs that we're going to be looking at in this chapter are no longer, let's say, position versus time graphs, but this is, see, this is vertical position versus horizontal position. This is technically our actual Cartesian coordinates. And when you have 2 points, point A, for example, then this point technically has, 2 positions that can be represented in terms of, let's say, XA and YA. All right, that means there is this, for position A, right? So then you have XA, and YA. And the same thing for position B. There is XB and YB. And object undergoing position change from A to B, all right, undergoing 2-dimensional motion. Basically, this displacement is also 2-dimensional. Now, the way we do here is this. So we have a reference point, which is the origin, right? So the origin is the reference point. And then we first look at position A. So I say, all right, so object here is at position A. Then I draw a vector from my reference point, the origin, to that position A. And I can say that now that's my initial position vector. That means this point A here is no longer on the x-axis or y-axis, right? Basically, this is on, some position where you have both horizontal and vertical, let's say, coordinates. Right, so then I have R sub A, R sub I. Then when the object goes from R sub I to R, from A to B, then I take B to be my final position and I draw a vector from my reference point to that, which is then this R final. And that's my position vector for the, for point B. So that's why RF. Then what I can see from here is things like this. So you have this first vector, Ri, and then the second vector, Rf, right? Those are represent vectors directly from the reference point to those A points A and B. And then when object goes from point A and B, I can draw a straight line from A to B. And this is this line over there. And that's basically my position change, right? That's how I change my position from point A to B. Remember, displacement here is always a straight line from your starting to your final points. Okay. So one thing then you will see from here is, let's say I'm pretty much constructing a sort of like a tip to tail, sort of like a configuration where R sub I is a vector, then delta R is connected to the tip of R sub I. So that means if I add delta R vector, then what I'm technically getting, graphically speaking, is delta, is this RF, right? Because see, RF connects from your tail of R sub I to the tip of delta R. That means if I add those two together, I'm technically getting R sub F, final R. All right, so now this is, kind of like a mathematical term. But what we do, we rearrange this. And I say, all right, so I'm going to take delta R and I'm going to move R sub I to the other side. So it becomes like R final minus R initial. And that's equation, technically vector form for finding change in position, delta R. That means to find this delta R, I need to then, as vectors, subtract final position from initial position vectors. And that's what we have, which is basically same thing as we did before, right? Delta X equals X final minus X initial. But now what we're doing here, we're doing in terms of, like, let's say 2-dimension. And position, right, when changes, we have to take into account both horizontal and vertical position change, simultaneously. So that's kind of like the thing that we have to do. That means we are technically looking at by how much, let's say, this horizontal position changed. So thing like this. So, let's say I have XA and I have XB, right? And I already also have YA and YB. That means this delta R right? This delta R is nothing but combination of these two. So let's say YB minus XB minus XA and YB minus YA. That means I'm looking at both of those simultaneously. Okay, so that's pretty much what delta R represents. I can even write delta R in a different format where I can say that delta R is equals to, so in terms of, then you can see, right, when I'm changing position, like let's say this delta R, I'm including both of those position changes in X and Y. So then I can technically say this is, when I'm changing my horizontal position and vertical position combined. That's another equation for then delta R. Okay. All right, so what else can we do with two-dimensional motion? Well, if you go from A to B, let's say, what I can do here is if I measure the time as well, then I can do the ratio, right? Delta R over delta T. That means I go from point A to B, measure the time, I get then this ratio of delta R over delta T. And this is, remember, it's just a V average. Ratio of displacement over time is V average. Doesn't matter if it's like one-dimensional or two-dimensional. That means in terms of then this particular, right, this particular, let's say, case, when you go from A to B, you are looking at average velocity going from A to B. You can look at then maybe B prime, then average velocity going to be like, let's say, from A, for this delta R2 or delta R3 and things like that. In a way, one thing we have here is, remember, those are basically our secant lines, and when you're finding them, the slope of those, right, you technically always going to get average velocity. Okay, that means we have delta R, which is technically delta X plus delta Y, right? So we're actually going to be later on representing them in this format, right? And then I have delta R over delta T is basically the average, which then can be represented as in terms of delta X over delta T. That means I'm looking average velocity in the X. That means like when I go from here to there, right? Not like this. So then I can look at, okay, so here's technically what I have. This is by how much I change my X. And this is by how much I change my Y. And then when I go from A to B, I can, technically, instead of delta R, use the combination of delta X over delta T plus delta Y over delta T, which means I'm, looking at each separately, but combining them to get delta R. All right, so then average velocity between points is independent of the path taken. Okay, remember, so technically this is true in a way that if I go back here, right? See, let's say when I go from A to B, I can technically go like this, that the path is given here. Remember, I'm talking about just from A to B. See, if I go from here like that, well, that's my displacement, or this vector here, right? That's my displacement, regardless if I took that path, or maybe if I go like this to that point, or if I go like that and come back to that point. My displacement's still all going to be the same. Why? Because displacement is only in terms of initial point, final point. I don't care how I got there. As long as, I know what my initial position is, I know what my final position is, and we draw this vector straight from A to B and use that to find then displacement. So that's why average velocity between points is independent of the path taken. Okay. So, and if particle starts its motion at some point and returns to its point via any path, its average velocity is 0. For this trip, since the displacement is 0. And that's also something we talked about. Remember, whenever you have a round trip, displacement is 0 because you come back to the same position as you started with. And that's also true for the two-dimensional. Here's point A. You start moving around and let's say and come back to this point A again. That's it. If that's your start point, that's your end point, your displacement is 0. Your distance is not. Distance, how much you moved around, but your displacement is 0. So your speed is not 0 because speed is average distance, average speed is distance over time, or speed is distance over time. But your velocity is displacement over time, and that's going to be 0. All right. We can also, let's see if you go back, right, and look at that in terms of like, let's say that B prime, B double prime, B triple prime, and you know, that means we're moving where those, you know, let's say, you know, delta T, right, getting closer. That means we're you know, that secant line, right, becoming sort of like a tangent line. Then we can look at in terms of, let's say, instantaneous velocity. So let's say this is my trajectory. By the way, this line that I have, this is not some kind of abstract position versus time graph. No, this is the actual trajectory of this object. That means in space-time, right? So let's say this is how it's moving. Where, for example, if I have a position versus time, if I draw this line, this is not how object moves, right? See, let's say the object technically moving from x initial to x final, like in a straight line in a horizontal axis. But the graph looks like this. Why? Because it's a linear motion going from x to t, and it's a sort of like an abstract graph because we're doing it as a function of time. But I'm doing this as a function of, you know, position. That means y as a function of x. That means how the object actual position every second changes in terms of its x and y, let's say, coordinates. So that's actual trajectory. Let's say, I don't know, maybe like a fly, you know, like let's say it goes around like that. And then, you know, I get a trajectory. Okay. So then what I have here is by choosing any 2 points, here's point A and here's point B. If I connect them, I'm getting the average. Okay. But as you see, because right, it gets closer and closer and closer and closer. At some point I have the tangent or the tangent, tangent, tangent. Those give me instantaneous velocities. That means whenever you have a graph like this, the tangent to the actual trajectory of the object can be used to find out the velocity. And that's, you know, for example, relatively easy way of figuring out what's going on. So for example, here's what I have. This is the velocity at that instant of time. And then here's the velocity of that instant of time. And here's the velocity of this instant of time. And you can see, right, this is basically a velocity at some t1, let's say, let's call this v1, right? And then this is v2 at time, let's say t2. What we get here is actually the direction of the velocity. That's the direction of the velocity, okay? That means it's, you know, you can break it down into components. So there's a vx, and then there's vy. So v1, v2x, v2y, and so on and so forth. That means this is actually the direction of the velocity, not some abstract, let's say, you know, idea. All right. That means, you know, you can say, right, the direction of the instantaneous velocity vector at any point of the particle's path is along a line tangent to the path at that point and in the direction of motion. So the magnitude of the instantaneous velocity vector is, remember, the speed. So the speed is always considered, you know, to be the magnitude of the velocity vector. Same way we can get the acceleration. All right, so the acceleration then will be change in velocity over time, which we know already. But this is, we assume that to be a 2-dimensional velocity now. That means, think like this. So what we have then this. First, we had position delta r. That means this is 2-dimensional position change. We can say that this is pretty much combination of both horizontal and vertical position changes. And then I have velocity 2-dimensional, which is technically then delta x delta t plus delta y delta t, which basically means this. This is vx velocity plus vy velocity. Why? Because, well, this is average. Because this is changing horizontal position only. All right, so what changes horizontal position? Only horizontal velocity. What changes vertical position? Only vertical velocity. That means you cannot have a vertical velocity change your horizontal position, or, you know, horizontal velocity change your vertical position. Okay, so that's why, for example, if I have velocity here, which is 2 meters per second, right? 2 meters per second I hat plus 2 meters per second j hat. See, this is a 2-dimensional velocity. It tells you by how much your position will change each second in this direction, which is horizontal, and by how much your position will change in that direction, which is vertical. So for example, if I'm graphing this x versus y, so for example, if you start from the origin, so if you start from the origin, right? So, sorry, this is y, this is x. I don't know why I did that. So this is y, this is x. So if you start from origin, it tells you that if you start moving, this is how you're going to be moving. That means every second in a vertical, in a horizontal direction, your position will change by 2 meters each second. That means 1 second later, our, let's say x, position will be here, x equals 2 meters. But at the same time, there is a vertical component to this velocity. That means it also makes object to move in a vertical direction 2 meters up. That means like this. That means instead of going like this or going like that, object is going to be, moving like this. So that's why when you move from here to there, this position means that you change your x by 2 meters and you change your y by 2 meters. So this is where you are. How about 1 second, additional 1 second? Well, additional 1 second means that you move another 2 meters in x, another 2 meters on y. So you're here. That means this is the object, how it's moving. Using this. That means every second, 2 meters in x, 2 meters in y direction, change. But why, for example, if you have something like this? Why if we have something like this, right? So let's say we have velocity equals, let's say 3 meters per second I hat plus 0 j hat. So what does it mean? Well, it means that this is a one-dimensional velocity vector. That means every second, so let's say thing like this. So here's if you have x and y positions, right? And let's say this is time. At t equals 0, let's say you're 0, 0, and then you start moving. 1 second later, your position in x direction will be 3. Your position in y will be 0. Time equals 2 seconds, your position will be 6 in the x direction, in the y direction 0. Then 3 seconds, into the motion, your horizontal position will be 9, and then vertical will be 0. Why? Because every second your horizontal position changes by 3. That means you are pretty much moving in one direction, or one dimension, right? You're just moving in horizontal direction. So that's why your vertical component is 0, even, let's say one-dimensional motion. But if not, if both of them non-zero, then instead of this or vertical up, you're moving like this. You're moving in a two-dimensional motion. All right. And this just tells you that if your velocity changes as you move in two-dimensional motion, that means you're moving faster, then technically your acceleration can be calculated from the change in velocity over time. All right. So here's a graphical representation of the velocity change as you go from A to B, which means that VI is the velocity at point A, V final is the velocity at point B. And what we can see here, right, there is a change in velocity. The question is that how is the change in velocity? It seems like VI and V final are the same length. But remember, velocity is a vector. And already the difference in A and B, you can see in terms of the direction. They're not in the same direction. That means different vectors. So remember, only if the vector in the same, two vectors, when two vectors in the same direction, in the same magnitude, then you can say they're the same. Same magnitude, but different direction, they're different vectors. And here you have two different vectors, V initial, V final. So then one thing we can do, we can find, change in velocity, okay? Change in velocity, right? Which will be, in terms of this. So the way you actually find, remember, so let's say this delta V, remember, is V final minus V initial, okay? So let's say, how do we do that? In previously, let's say chapter, we learned that we can change it to like this. So V final plus negative of V initial. So we can technically do that, that's what we're doing. See V final, so we have V final, and then add to V final negative of V initial, which is this guy here. And then tip to tail gives us delta V. This is tip to tail method. That means when you're using tip to tail method, right, you then connect V final and negative of V initial together, tip to tail, and then the resultant delta V goes from the tail of V final to the tip of negative V initial. Or you can use a parallelogram method. Okay, so for this one, we basically, or you can see, right, we are rearranging to this. Remember, delta V equals V final minus V initial. You can also say then V final is equals to delta V plus V initial, right? That means if you add delta V and V initial vectors together, tip to tail, you can see, right, tip to tail, then V final is then the resultant, and that's what we get. That means the difference here is technically can be represented like that, two different ways. All right. So again, same way, we can say that acceleration, if we take the limit with the delta t approaches 0 for the ratio of delta v over delta t, this becomes dv dt. All right. Again, so it's important to understand, let's say, when the acceleration or velocity, let's say when you use the derivatives, when you actually have to use those equations compared to when you use the general kinematic equations. Well, think like this. So if you're given x, so like in terms of, okay, so here's my x initial position, which is 2 meters. Here's my final position, which is 5 meters or something like that. Well, there is absolutely no need to do any derivatives here. You do that when, let's say, x as a function of time given, sort of like, let's say as maybe like, I don't know, 5t cubed or something like that. So this is then when you need to do the derivatives, because here you are given initial position and final position, okay? Here you're given how the position changes as a function of time, because things like this, x when time is 0, position is 0. X when time is 1, position is 5 meters, right? And x when time is 2, then this is what? 8 times 5, so 40 meters, right? So like, and so on and so forth. That means you are getting function where the t, let's say dictates what the position of x is. When t is changing, x is changing. Then here we can then say, okay, so then velocity equals dx dt, all right? So this could have been even like this, right? It could have been like, let's say r, as a function of time or something like that, right? So you can say then the delta v equals delta r delta t or thing like that. So, and take this as, let's say 15t square, and then when you find the acceleration, and then basically you take the derivative of it one more time, so it becomes, let's say 30t and something like that, right? So, and each time you can take the derivative. There's no way to take a derivative of that one, right? So, but when you're given something as a function of time, then you can do the derivative. Same way you can, say that velocity equals to integral of a dt, right? Going from t1 to t2, and take the integral of the acceleration to go back to the, let's say velocity. All right, so anyways, so what we have here is this. So the various changes in particles' motion may produce an acceleration. Okay, so this is basically, how we define acceleration when we're in this chapter or in the previous chapter. Magnitude of velocity vector may change. That means speed is increasing or speed is decreasing, means that there's acceleration. Or the direction of the velocity vector may change. That means you have a velocity changing direction even if the magnitude is the same. That means even if the speed is the same, right? You change the direction, you already have a change in velocity. What does it mean to have a change in velocity? It means that there's acceleration. So you can have either one of them or both of them at the same time. Okay. Now, motion in 2 dimensions can be modeled as 2 independent motions in the x and y direction. Because as the object moving, you can independently track only the horizontal variables. Let's say horizontal change in position. So let's say thing like this. So here's the object that actually moves like this. This is in a y versus x position. But what I'm doing here is I'm looking at, let's say, just horizontal change. I'm looking at x initial, x final. And what I can do from that, I can calculate delta x, x final minus x initial. I can take the ratio of this one with respect to time and calculate Vx, right? And if the velocity at x initial and x final are different, then I can, remember this is average velocity, right? Then I can basically calculate horizontal acceleration, which is change in horizontal velocity over time. This means this is just only in terms of x. But then separately from this, I can look at vertical everything. I can look at delta y, or let's say Vy average. Or let's say I can look at AY, which is then delta VY over delta T, and so on and so forth. That means I can treat them as 2 independent motions. And if I need to put them together at the end, well, one thing going to be true for them, let's say in X and Y direction, even though they're independent, one thing that is exactly the same for both of them is this delta T. Delta T is the same. That means how long it takes to go from here to there, exactly the same time it takes to go from here to there. right? That means by how much you change your x is exactly by how much you change your y, and the delta t, right, the time interval is the same for both dimensions, okay? And they are not, let's say, affected by one another. It means I can completely, as I said, right, independently look at only x motion, then independently look at only y motion, but then, you know, connect them whenever I need to, right? Let's say if I want time, or if I find time, I can use the time in the x direction motion, or, you know, because it's the same for both of them. And that's something we're going to be doing a lot, especially when we get to what we call projectiles. All right, so we can also use unit vectors. So that means, for example, vector r is a two-dimensional position vector. But, you know, think like this. So let's say I'm talking about point A, right? So this point A is some position that is not on the x-axis or on the y-axis. That means I draw a vector like this, and I say this is vector r. But I understand this vector r is also equivalent to its projection on the x-axis. I can say that this is rx, and its projection on the y-axis, and this is ry. So rx, ry. And you can see, right, I have a tip-to-tail method where rx and ry are the sides of a triangle, r is the hypotenuse. That means I can say vector r is then rx plus ry. What is then rx? Rx is just represents change, you know, change in x, right? So I can just say this is x, assuming that we start from the origin. So I can say it's x I hat and plus y j hat. That means it has x and y components, right? Which it does, right? To go to A, I can either go along the vector r, or I can go along the x and y, doesn't matter, like, or y and x, right? And get to the same point. Which means that if I then think like this, if I'm taking a derivative of r with respect to time, which means I'm taking the derivative of each one of them with respect to time. So that means, you know, v equals the derivative of r is time with respect to time. Then I have the dx dt I had plus dy dt, you know, j hat. What is dx dt? Well, dx dt is nothing but vx, because vx is the horizontal velocity responsible for only changing horizontal position. Vy is the vertical velocity only responsible for changing vertical position. So that's why. That means I can write everything from this, you know, two-dimensional point of view, right? It's a two-dimensional vector. That means it should have x and y components. Two-dimensional vector should have x and y components. How do we get x component of the velocity? Well, taking the derivative of the x with respect to time. How do we get y component of the velocity? Well, taking the derivative of the y component of the position with respect to time. All right. And this is kinematics 1, if you remember. It's just written in terms of like a two-dimensional vector. That means we're assuming that v final is two-dimensional, v initial is two-dimensional, and acceleration is two-dimensional. And this is nothing but kinematics 2, again, written in terms of two-dimensional variables, right? So sometimes you can actually, if you've given everything into component format, do directly, let's say, two-dimensional vector calculation for the kinematics. But I would say that you are always better off just to separating any two-dimensional motion into x and y axis, and then doing them separately, and then at the end combining whenever you need to. And there, you know, there are several examples that I'm going to be doing, you know, for, like, let's say, different versions of that. Okay. So you can see, right, this is in a way what we have, representing, like, let's say, the graphical method of those two equations. See over here it says v final as a vector is a combination of v initial as a vector and the product of acceleration and time. And that's what I have, right? So v initial as a vector and a product of acceleration and time as a vector, then you get v final. And this one is basically, you know, the same thing for the equation, kinematic equation 2. All right, let's look at an example here. So this example, it takes a sailboat that is traveling east at 5 meters per second. So sudden gust of wind gives the boat an acceleration of a, and we're given the magnitude of 0.8 meter per second square, and then 40 degrees north of east. What are the boat's speed and direction 6 seconds later when the gust subsides? When the gust subsides. All right. Let's see what we have. I think I have like a nice diagram. There you go. So we have a boat that initially let's say we take it and place it at the origin. So let's say here's the boat initially. So you can say, right, we have the position. So here's the initial position, x equals 0, x initial, y initial. By the way, remember, right, x initial, I can write it also like this. I can write it also like that. Or sometimes I can write as x1 to indicate x initial. But that just means that initial position. So you can see, right, because it's at the origin at t equals 0, then all of the initial variables of position, horizontal and vertical, is exactly 0. But I also have the boat moving with initial velocity of 5 meters per second east. And remember, if I write down the general equation, I have this, right? So v initial x I hat plus v initial y j hat. But what I have here is I have then 5 meters per second I hat, east is I hat, right? But then 0 meter per second j hat. That means I had no initial vertical velocity. But then there's acceleration. Here's the acceleration as a vector. And it says it's 0.8 meter per second square, 40 degrees north of east. What it means here is that this is basically a two-dimensional vector acceleration, right? Because I have kind of like this, right? I have magnitude 0.8 meter per second square and 40 degrees north of east. So if I'm plotting this acceleration, it will be like this, 40 degrees north of east, east, north, which means if I'm writing this as ax I hat plus ay j hat for acceleration, then I have then, let's say, 0.8 magnitude times cosine of 40 for the I hat direction component plus 0.8 sine of 40 for the j hat component, right? Then let's see what we get. If I'm doing this calculation, then I'm for the acceleration, then I'm going to get this. The x component end up being 0.613 meter per second square I hat plus 0.514 meter per second square j hat. That means, using those, right, product of magnitude and the position, right, so like a direction, I get those. Okay. All right, so what else do we have? Well, we also have the final time, right, which is 6 seconds. Now, here's then what we have. You can think of like this. Here's the boat, right, sailboat, moving with horizontal initial velocity, but then there is a wind, and the wind gives it an acceleration like that. That means acceleration will then change this velocity. What it means is that, remember, here's the acceleration vector. And what it does here, it tells you that this is by how much your x velocity will change each second. This is by how much your y velocity will change in each second. That means eventually what we're going to have an object with a velocity that, going to change both in x and y direction. Okay, both in x and y direction. Now, here's one thing we can do. I can separate this into horizontal and vertical motions, but I can also, do like, let's say, direct two-dimensional calculation. Remember, v final as a vector equals v initial as a vector plus acceleration times time, right? Acceleration as a vector then times time. Let's see what I have. V initial was 5.0 meter per second I hat plus 0 j hat, then plus acceleration of 0.613 meters per second I hat, then plus 0.514 meter per second j hat, then times 6 seconds for the time. Okay. Now what I get here is this, right? 5 meter per second I hat plus, then I do 6 seconds times 0.613, then 6 seconds times 0.514, right? So basically, distribute like that. And let's see what we get from there. 0.613 times 6. I get 3.678 meter per second I had, because acceleration, remember, sorry, it's acceleration times time, we cancel one of the, seconds, right? Then plus 0.514 times 6 seconds. Then I get 3.084 meter per second j hat. All right, so what I have here is this. I have two terms with I hat and one term with j hat. And hopefully you guys can see, right? Those two I can combine, but I cannot do anything with the last one over there. That means what I can do here is this. I can combine those 5 and 3.678. So let's say get 8.68 I hat. Let me do units, not forget that. Meter per second I hat. Then plus 3.0 rounded, so let's say 0.9 meter per second j hat. So that's my final velocity in terms of its components. That means I can directly find its components. Okay. So this is the velocity in terms of its components, but we want the speed and the direction. But it's easy now because remember, this is Vx and this is Vy. And then let's say V final X, sorry, and V final Y. Then V final will be, square root of those. That means it will be 8.68 square plus 3.09 square, and I can find this to be 9.2 meter per second. The direction, well, I use inverse tangent of 3.09 divided by 8.68, and I can find that this is 20 degrees with respect to positive X, so I can just say northeast. 20 degree of, north of east. And that's my answer. And that's, you can see, right? I didn't separate them into sort of like, let's say X and Y separately, right? I actually used the component method, which technically implies that there's a separate X and Y, but I put everything into just one equation. Okay. So in a little bit later on, we will see that we can technically, when we're dealing with projectile motion, do opposite, which is separate them into X and Y, and then work with two separate coordinate systems. All right, here's one more example. So we have a particle's trajectory that will be is described by the two function x and y. So you can see x is 1/2 t cubed minus t2 square, and y is 1/2 t squared minus 2t meters each one, where basically quantity, everything is in meters and the t is in seconds. So then what are the particle's position and speed at t equals 0 second and at t equals 4 seconds? So we need to find those informations. So to start with, we take this x as a function of time, which is then, 1/2 t cubed minus 2t squared. Okay, so we use this, remember, we want to find position at t equals 0. So then you can see that if I then take t at 0, t equals 0, then it becomes 1/2 0 cubed minus 2 times 0 squared, which means it's 0. Same way for the y as a function of time, it's 1/2 t squared minus 2t. So then if I do y when time is 0, becomes 1/2 times 0 squared minus 2 times 0 also equals to 0. So conclusion here at t equals 0, we can say then r, right, is 0 I hat plus 0 j hat, which means it's, at the origin. All right, so then let's look at the next one. Okay, so the next one would be at 4 seconds. So for that, we do x when time is 4 seconds equals 1/2 times 4 cubed minus 2 times 4 equals 2. Well, if we do that, let's see what we're going to get. So 4 cubed is 64. And all right, so there was a square over there. So 4 cubed is 64. So then 1/2 of 64 minus 2 times of 16. So half of 64 is 32 minus 2 times 16 is 32. So basically we get 0. All right. Then y at 4 seconds is 1/2 times 4 squared. Remember, I'm using this basically. Then minus 2 times 4. So for this one, I get, so 4 squared is 16. Half of it is 8. Minus 2 times 4 is 8. Well, I get 0 again. That means at t equals 4 seconds, my position is also 0 I hat plus 0 j hat. So what does it mean? Does it mean the object didn't move at all? Well, we don't know yet at this point, but we know that 4 seconds later, we're exactly the same position as where we started. Okay, so now let's look at in terms of the speed. Okay, and that can kind of tell us something. So at t equals 0 and at t equals 4 seconds for the speed, well, I need equation for the speed. So we take then and use, a velocity vector, right? So in terms of, like, let's say vx I hat plus vy j hat. Okay, that means this is my, speed in the x direction, speed in the y direction. Now then, what is the speed is in the x direction? Well, it's dx dt I hat plus then dy dt j hat. Okay, that means I have to do those, derivatives of each one. So then let's see what I had. So for the Vx, I get dx dt. That means I take the derivative of the x. So what I'm going to get here, if I look at it, becomes 3/2 t squared minus 4t. Right, 3/2 t squared minus 4t for the x. In the y direction, I have then dy dt, which is then taking the derivative of this guy. So it will be 2 over 2 t squared, 2 over 2. So 2 over 2 times t, so this just becomes t, minus 2t, so it becomes just minus 2. The derivative of this one is just this. All right. That means I can say then, for example, v here is 3/2 t squared minus 4t I hat plus t minus 2 j hat in terms of this. All right, so then what I'm going to do here is this. I'm going to use each one to find, x and y at t equals 0 position. So let's say then vx when t equals 0. So then it will be 3/2 times 0 squared minus 4 times 0. Well, I get 0. All right, that means it has no x component. Does it mean there's also no y component? Let's see. Vy at time equals 0 is equals to, so here's t, so it's 0, minus 2. Well, we actually get minus 2 meters per second. That means technically v at t equals 0, right, is 0 I hat, but minus 2 meter per second j hat. That means we are actually be moving at that instant of time at t equals 0. So there is a downward velocity. That means we start at the origin, but there's a downward velocity. All right, there's a downward velocity. Okay, let's see what else we have. We want also t equals 4 seconds. So kind of do it similar way. Vx when t equals 4 seconds, let me do it like this. When t equals 4 seconds equals to. So now I do 3/2 times 4 square minus 4 times 4. That's basically for the x component. And if I calculate this, I'm going to get, let's see, 8, right? So 8 meters per second. So basically 4 square here is 16. Then if I do 3 times 16, I'm getting 48. 48 divided by 2, I get 24. Okay. And 24 minus, this is 16. So 24 minus 16 is then 8. There you go. Then Vy at equals 4 seconds is equal to then. So I do 4 minus 2. Well, I get 2 meters per second. All right. That means V at t equals 4 seconds is 8 meter per second I hat plus 2 meter per second J hat. Okay. All right, so we have those. Now, one thing I can do here is this. Remember, I want the speed. How do I find the speed? Well, so think like this. If I have, let me use this as equation 1, I guess. So, or let me do it like this. So I'm doing for this guy. I want speed at t equals 4 seconds. Well, what I use here is this equation. V is equals to square root of x squared plus y squared. So it becomes 0 squared plus 2 squared. Then 2 squared is basically going to give me 2 meter per second. So this is, let's say, V initial, which is at t equals 0. And then for the same way I can do for the V final here, right, which is basically 4 seconds later. So this is then square root of 8 squared plus 2 squared, and that's going to give me 8.3 meters per second. So that's the speed for 0 and 4 seconds. All right. So we needed to find a couple of things. Position at 0 and 4, and then the speed at 0 and 4. And that's what we got. All right. The last thing we want to find in part B, it says, what is the particle's direction of motion measured as an angle from the x-axis at t equals 0 and t equals 4 seconds? All right. So I have just a little bit of room, and I'm going to utilize that because we don't really need much. So here's my coordinate system. So think like this. What I have here is, let me use red. So initially at t equals 0, it's asking to draw the velocity vectors pretty much. At t equals 0, remember, we have this as a velocity vector. That means just a negative, 2 I hat. Okay, negative 2 meter per second I hat. Then at t equals 4 seconds, our velocity is this guy here, which means then we got that 8.3 meter per second magnitude. That means it's going to be 8.3 meter per second, which is about 4 times longer than this guy over here. But we don't have the direction. That's one thing we don't have. But we can then use the direction using the components. So let me do it here. So just inverse tangent of 2 over 8, y component over x component. So we're going to get 14 degrees. That means that at the time of 4 seconds, the velocity is going to be something like that. All right, so that's not accurate because that's not 14. So maybe it's something like this. There you go. About 4 times long. So this is V final, and this is V initial. All right. So, and let's say, assuming that this is 14. So kind of like, then what do we have? Well, I imagine that this object probably within that 4 seconds goes like this and then comes back and goes like that, right? Because there's no other way it can come back and have a in that direction velocity. See, if it goes like this, the velocity would have been in this direction, okay? That means that's not accurate. So it has to be going down and then turning and coming and moving at 14 degrees at the origin at, when it passes there at t equals 4 seconds. All right, then this is basically that particular one.